So good morning, everyone. I'm Chris Jones, GM at Vicom, and I'd like to thank you for joining us today in another of our series of technology training webinars, this time on precision, time and frequency. Vicom is Orolia's partner in Australia and New Zealand, and we're working closely together to bring you this webinar today. The idea behind the webinar came from internal training at Vicom's engineers some months ago. We're all experts in electronic engineering, radio communications, telecom engineering, or say IT, but frequently I find we've skipped learning about the fundamentals of precision, time and frequency that affect all of those technology areas. That's what we're going to address today. So now I'd like to introduce you to our presenter, Morgan Randolph, Applications Engineer at Orolia, who is based in Rochester, New York State in the US. He's an analytical problem solver with over 20 years of providing comprehensive enterprise-level on-site and remote technical support. He's a solution provider to complex network connectivity, RF and related applications issues, and a service professional focused on Fortune 500 and international clientele. So over to you, Morgan.
Thank you for the introduction. Yes, I've been with Orolia for seven years. Started my 8th year in January. I worked in customer support and currently has been an application engineer for the last 2 years. Today, we're just going to give you an introductory to the timing and frequency piece. We'll touch some Ntp, Ptp, just some general overview stuff, and if you got questions, like you said, just ask them, type them in the queue. So we'll get started. Thank you. Time. Time is the most accurate physical quantity. So basically, 9 billion, there's over 9 billion oscillations of a cesium atom, and that's how we come up with the UTC time. NIST is the National Institute of Science and Technology in the US. They provide time, so you can go to the NIST website and anybody in the world can go to the NIST website and actually point to the servers and grab time for your environment, for your PC, for your any application you have. The US Naval Observatory is they're the administrator of all of that. They're the official timekeepers. Paris has one, it's the BIPM. They keep the time in Paris, and I believe Australia has started doing over the last 4 or 5 years. They've done that. So what is UTC? UTC is the Universal Coordinated Time. There's a couple times, there's a couple other time, I guess a couple other, not protocols, they're not protocols, but other time factors. So you have GPS time, which is UTC as of 1982. You have TAI time, which is International Atomic Time, which was created in 1967. So with that said, you also have the leap second. So the GPS time is 18 seconds difference than UTC, and TAI time is 37 seconds difference than UTC. What that means is that we've had leap seconds, and as those leap seconds happen, that time changes. So the last leap second we had was I think 2 years ago. The leap second, we don't have one coming up, but if they do have a leap second, typically they're done in June and December, and they'll give you 6-month notice that they're going to do a leap second. The reason why they do the leap second is because the Earth is speeding up or slowing down. You can actually take away time or add time. Since I've been here, they've never taken away time. We've always added time. So that will change that difference between that. So next time we get a leap second, it'll be 19 and 38 for the TAI and the GPS. Frequency. In mathematical terms, frequency is the first derivative of time. Oscillators and clocks. So you have oscillators like right here. You have clocks. You have the counter, you have oscillators, you have the time display. So with the oscillator, you have 1 second equals a hertz. 1 second equals a hertz. You got millions per second equals megahertz, and billions per second equals gigahertz. There are a number of types of oscillators. The MEM type is the least accurate, I guess I would say. It's, I believe it's mechanical, electromagnetic. The first word I got is wrong. It's electromagnetic, mechanical. So it's like a mechanical oscillator of some type. There's quartz crystals. There's atomic oscillators, which are rubidium and cesiums. There's hydrogen masers, active and passive types, and optical clocks. So as you can see here, the oscillator is providing the oscillation. Your counter, the oscillations go into the counter displays the time, and you have your frequency output from the oscillator. This is just a quick graph to show you, or display to show you the cost of the accuracy, the cost, and the size of the different types of oscillators. So if you look at the TCXO, which is what we sell in our products, we sell the TCXO, the OCXOs, and rubidiums within our products. You're looking at a chip. It's about $5. It's a bigger chip than the XO watch, but it's a chip just the same. Then the OCXOs is a module. That module is about $100. If you go to the rubidium is about $2,000, and it's a bigger module. In our case, it looks like about the size of a cigarette pack. A little metal container that's got the rubidium electronics in there, and the rubidium itself. When you get into the hydrogen, or when you get into the cesiums and the hydrogen masers, you have, I mean, those are huge types of oscillators. You're looking at 20K and 250K. We've got a cesium in our office. It's a 2-rack space type of device. Never seen a maser, but you're looking at the cost, and you're also looking at the accuracy. So you go from 10 to the -4th to 10 to the -16th for your accuracy. So there's a big difference. So you basically, the more accuracy you want, the more you pay. GPS discipline clocks, most accurate and cost-effective way of obtaining let me move my picture out of the way here. UTC time and precise frequencies is from GNSS satellites. So the GNSS is all of the satellites up there that are currently there: GPS, GLONASS, Bidet, and all the rest of them that are there. So they provide basically time right from the satellite systems right into our device or any other device out there. And then that oscillator is disciplined. And that's how the oscillator is disciplined. And we use phase lock loop to discipline the oscillator. And you provide a Kalman filter within that. That's all part of the electronics, not that much. I guess the big thing is the holdover. Trained oscillators maintain accuracy over limited periods of time without GPS. So in the case of our rubidium, we take, for us, it takes 2 weeks basically. If you're disciplined GPS for 2 weeks, once you have that 2-week window, that basically the heating and the warming of the oscillator control gets it in a, I guess what I call a static state where it's working as prescribed and doing things at the sweet spot. From that point on, if you were to lose your GPS, you could have it in holdover for probably up to 5 years without losing a second. You'd lose time, but you wouldn't lose a full second. It'd take about 4 or 5 years for you to lose a full second. There's Sasum oscillators. Basically what that is, selective availability anti-spoofing modules. So they're controlled by the US government. They're using mostly military applications. I would say 99% of them. They're easy to jam, but hard to imitate. What I would do with the cesium, those are something that you've got to get requests from the US government for. I know some of our NATO partners and other European countries have used the Sasum, so it just depends, but it's all controlled by the US government. Time is distributed from a number of different types of protocols. You got your regular PPS, the 1 PPS, which is 1 pulse per second UTC. You've got the iRig. You guys are probably familiar with that. The interrange instrument group, that adds time of day to the stream. It's a 50-year-old spec, so it's been around forever. There's a lot of variations of it. You've got STANAG, the standardization agreement. That's mostly used in Europe. So you have half-quick, you've got other time codes like ASCII, NEMA, time of day, and the PPS, all provided through that STANAG cards. We have all of those cards that are available within the Secure Sync units. You have the Ntp protocols, and you have the Ptp protocol, which is the IEEE 1580. And as you can see, you're looking at milliseconds within the thousandths, and microseconds within the millions, and nanoseconds within the billions. And if you want to compare these different protocols on the left here, you're looking at 1 to 10 milliseconds on the for Ntp. You're looking at less than 1 microsecond for iRig, greater than 1 microsecond for Ptp, and GPS is going to be 10 nanoseconds, along with PPS is going to be 1 to 10 nanoseconds. So you can see you're going to get Ntp is the most used probably, but it's the least accurate of, or the least, I guess, the most time of all of these different protocols. So it really comes down to, when you're asking your customers, you just need to understand what their needs are, what their accuracy needs are, and what their holdover needs are. And that will help you to determine which way to direct them, whether they want to go Ptp, iRig, GPS, Ntp. Frequency distribution can be done through all types of cabling. So typically you're going to see it through coax, probably RJ58, 50 ohm termination, provides a sine wave, 10 meg, 1 meg, 2 meg, 5 meg. You can do twisted pair. That's going to give you a lot of your communication stuff for your frame, your super frames and stuff like that. So your E1, T1 stuff. Then you've got wireless, and you've got the LAN, the Cat5, which is going to get into your synchronous Ethernet. So that's going to be, if you look at this here, it tells you Ethernet carrier clock is recovered and passed along down the chain. So as you jump nodes, you go from node 1 to node 2, node 3, that timing, that syncy information is passed along. So the timing is maintained throughout that whole system. A couple of the things that you need to be aware of, and this dictates again back to which oscillator you may want, or which protocol you'll want to use. But you're looking, most often you want to find out how accurate the customer wants to be, how stable the customer wants to be. What you're looking at is, if you were to use one of those Gnss servers, for instance, it's a stable protocol. You're using Ntp, but because it's not controlled within your data center or your environment, it's not going to be the most accurate, because you're going to have, one time you may have 10 hops to get to your site, and the next time you may have 20 hops to get to your site. So it's not going to be accurate. So what our device provides is, down in the right-hand corner here, we provide stable and accurate timing solutions. You could have not stable, not accurate. You could have accurate, not stable, stable, not accurate. You'll get all of those from varying degrees to varying oscillators in various ways you're trying to get time. This is just the mathematics that they use for the Allen variance. Is really nothing important here, nothing that your customer is going to be asking you about, really. But jitter and wander. Other useful measurements of stability. So this is going to be how you measure the stability, or at least a couple of aspects of the stability, are the jitter and the wander. These are measures of the phase error of a digital clock signal in comparison to a reference. So it's going to be, if you're using GPS as your reference or GNSS as your reference, that jitter and wander will be compared to that. If you're using NTP, the jitter and wander will be compared to the NTP. So when you look at jitter, jitter is phase modulation of 10 hertz or greater. If you're looking at wander, wander is phase modulation slower than 10 hertz. So basically your sine wave is going to get compressed, or it's going to get shorter, and it's going to create, it's going to affect your stability within your measurement, or create noise within your clock, or delay. I mean, there's a number of ways that's manifested: delay, noise, jitter. That's all going to affect the timing and how accurate it is. You've got phase noise measured in decibels, is logarithmic. It can be also measured in watts, milliwatts, and a center frequency. This is just really, I guess the most important line here is the quartz crystal oscillators change frequency under acceleration. So if you are in a type of where you're in a vehicle or in a sub or in some type of motion as opposed to sitting in a rack, you're going to have the effects of that acceleration, and that vibration is going to impact the oscillator, and it's going to cause phase noise. So you'll want to take that into consideration as you speak to the customers about what their needs are, or as they express what their needs are. You'll understand that they may be doing a motion type of drone or something like that, where they're providing these, where they're providing time, but it's going to have some effect. The acceleration is going to have some effect. We've tested to quite a few of the specifications, but we haven't done all of them because it's costly to do that. But just ask the question and we can provide the information, the testing data. We've done quite a few of the mil specs. Let me introduce you to NTP, Network Time Protocol. Internet protocol used to synchronize clocks of computers and other NTP-enabled equipment. Basically, this is written back in the probably the early 70s, mid 70s, is when they came out with this to be able to keep time for your computers. That's where it all started. The network time protocol, network NTP is needs a reference clock that defines the true time. So we'll talk more of that as we go through the presentation, but the reference clock is the internal clock within our device that gets the time right out of the satellites. It uses UTC as the time reference. So even though we can provide TAI time and we can provide GPS time, it uses UTC as the time. So we've had customers have the wrong time, said, hey, I'm 37 seconds off because they've got it set for TIA. I'm 18 seconds off, or 8 seconds off because 18 seconds off because they've got it set for GPS. We come out the box right for UTC. NTP is fault tolerant, it's highly scalable. We'll touch on some of that as we go through the rest of the presentation. Can select the best candidates to build its estimate of the current time. It uses measurements from the past to estimate current time and errors, and maintains estimates of the accuracy of the local time. So on our device, on the secure sync, you have a window that shows you, out the box, it defaults to UTC time, but you can show the local time if you choose to program it and set it up that way. Basically, there's a lot of flexibility there. NTP version 4 is the latest version. We support the other versions of NTP. I think there's a 3 and there's a 2, but most 99.5 or 9% of anything that's out there is going to be NTP version 4. NTP uses the UDT UDP port 123. So one of the things that's interesting about NTP is the stratum hierarchy. It was confusing when I first got involved with timing 7 years ago. I knew NTP, but I didn't know stratums or anything. So the stratum level is the number of steps that a system lies from a primary time source. So stratum 0 would be the satellites, are in the case of our device, we have a system clock, an internal system clock, and that system clock, the reference clock is what it's called, that system clock within our device gets its time from the GPS. And we provide out of our box, we provide stratum 1 time. So when you look in our web interface, it'll be a stratum 1, it'll say stratum 1. It can say stratum 2, it can say stratum up to stratum 15. But what that does is it tells you how far away you are from the source. So example would be if you have our device set up in the data center and you're pointing to another one of our devices, you would see the one that's connected to GPS would say stratum 1, the secure sync server that's connected to the stratum 1 device via NTP would say it's stratum 2, and then your clients, they wouldn't say it probably, but your clients, your computers and so on and so forth would be a stratum 3. The same thing would apply if you are pointing your switches to our device. So if you have Cisco switches, you point them back to our secure sync, the Cisco switch becomes a stratum 2 device. And as it provides out to the different clients or to your servers, or it may provide to all your server infrastructure, your DHCPs, your Active Directory servers, when you look at that, those will be stratum 2s, then the clients would be stratum 3s. The Cisco switches would be stratum 2s, the servers would be your stratum 3s, and then your clients in that case would be stratum 4s. So the purpose of this is to avoid synchronization loops by preferring servers with a lower stratum. And that gets into some of the design and some of the other aspects of the NTP protocol and how you're setting this up. You've got modes of operation. You've got the client server side. The client gets time from the higher stratum servers. That was an example kind of that I just gave where you have the servers providing times to different clients. The client does not give any time back to the server. It just requests time and says, hey, what time is it? And the server replies. In a peer-to-peer type of situation, the clients and servers are all at the same stratum level. We don't do peering at the stratum 1 level. That's not recommended. But at the stratum 2 level, you can do that at the stratum 3 level. So in the first example I gave where I said you have a GPS device, and then below the GPS device, the stratum 2 device, which is just strictly NTP, there's no GPS to it. Then you might have 3 locations that have that same setup. 1, 2, 3, data center A, B, and C. All of those stratum 2s, you would peer to each other in case one of the data centers went out. Those stratum 2s, those are the ones that are connecting to your clients or to your rest of your other infrastructure. And they would actually maintain their time, even though you may have lost GPS in one of those locations because of the peering. NTP does broadcasting, it does multicasting. They're essentially the same. Most of the time, you don't see that in the corporate networks because that just creates too much traffic to broadcast it out. Usually, 90%, 100% of the time, most of the people are doing server client server type of situation. You've got the minicast where allows auto discovery of servers and auto selection of the best 3. So there's some things around that. There's some software in that, and it works with your switching infrastructure a lot of times to provide that. You don't see that much, but we do provide an Anycast solution for customers that may want that. You've got NTP operation. You've got a daemon, so the NTPD. the daemon processes that is both client and server. So that daemon you have, you'll see that if you were to run an NTPD at the command line, you see the results of that for both the client and the server. And then you've got the monitoring devices or monitoring at the command lines. You got NTPQ, NTP DC, and that allows you to monitor some of the things that are going on within the NTP protocols. Initialization, synchronization, when you're doing NTP, and so in this instance, really what we're talking about, just to give you the framework, is you've got a device up at the upper level, which is connected to GPS. Then you've got these devices that are Stratum 2 devices that are just talking NTP back up to that Stratum 1 device. And that's what this is, that's kind of what we're talking about as you're looking at these things and you're looking at the monitoring and you're looking at setting up from here on out. That's how we're going to be looking at that. We're going to be looking at the NTP side of things. So with that said, you've got, as you set this up and provide the different parameters that you're looking for, it takes about 5 minutes to go through the polling and the accessing and the testing that it does within the algorithm. It takes about 5 minutes for everything to go into sync. You can use the iBurst to try to make it happen quicker. We'll show a slide. I'll show you a slide later that shows you the parameters that you have within that when you're setting up an NTP server. So NTP operation, it provides time stamping. You can see the offsets, you can see the delays, you can see this model, or the way it's set up, assumes a symmetrical network path. So this way, you know, you're in a data center and you're doing this, and you can get those offsets and delays easily. If you were going to a Gnss environment and grabbing your, because you would be a Stratum 2 if you were using the Gnss servers out there, that's not so much a symmetrical type of environment. That would be asymmetrical because you don't know how many hops you're going to take each time you go and make a request. So when you have your own, or when a customer has their own time servers, it's more of a controlled environment, so you know the network path. So to measure offsets, you take the T2 minus the T1 plus the T3 minus the T4 divided by 2, and that's going to give you the offset from the mathematics side. The delay would be T4 minus T1 minus T3 minus T2, and that will give you your delay. It usually, you know, these are multipliers of always a power of 2. So the polling interval, and you'll see, we'll show you in that slide where you can set up your min and max poll. The polling interval, with the polling interval, the jitter should not exceed the wanderer. So as we look at the rest of this, you'll see what that means in terms of how NTPs, the algorithm within the NTP work. The polling interval adjusts to values within the min max poll variable, and they're configurable. Now this is the system clock that I was talking about, where within our device, we have the system clock. The system clock is updated by NTPD in small quantities. So correction values are applied less often to stable clocks. So basically, NTP typically slews to bring your time in. So when you open up a box, you plug it into your network, you're providing time to the network at this point, you're getting it from GPS, it starts to slew. And it takes the time that was already there, and it looks to see where it is with the GPS and the location. And depending on how far off it is, it slews in. So that's the slew. That's a gradual change of time. But if you're way out, so let's say you're over that 128 milliseconds, the 128 milliseconds, it's going to do a more aggressive aggressiveness to try to bring the line your time up real quick. So what's going to happen is it's going to do steps. And I don't remember the math behind the steps, but it actually does a step. And then if it looks again, it says, hey, you're still over 128, it's going to step again, it's going to continue to step. And till it gets to the point where it's below that, and then it will start to slew at that point. So that could take some time to go through those steps. It could take you 60 minutes, an hour, depending on how far off you are. Could take a longer. One of the ways to get around some of that is to bring you back into that slew area would be to start and stop NTP. When you do that, what that does, it automatically starts to disciplining right where it sees that it was, and it will start to bring it back in closer, and you'll start to slew, so you won't be that far off from where you won't be that 128 milliseconds off. The Ntp Service Election process, we kind of touched on it earlier, but it's how the algorithm works. Ntp estimates the error of all clocks it reaches. So when using multiple time servers, Ntp calculates an error interval where the correct time must be when the time sources that are reachable and have a jitter smaller than the maximum become candidates for synchronization, thus contributing an error interval. I'm going to read these first, and then we'll kind of go back and take you through them. If these candidates pass another validation test, they become survivors. Basically, all values must lie within the error interval the majority of the candidates define. All other time sources are called false tickers subsequently, and among the survivors, those with significantly high jitter are removed. So what happens is the algorithm, it says, hey, let all of the clients are sending information, are requesting information, and they're looking and saying, hey, this device doesn't appear to be that good. This device appears to be better. These 5 devices over here appear to be a little bit better. As they survive that process, it continues, and that's where you get into the second thing I read there, where you become a survivor. And then as they really try to start to isolate get closer to the timing, the correct timing server or the right time server that they want to use, that's when it says, okay, what else we got here? Oh, the jitter's off. So if the jitter's off, we're going to get rid of you, okay? The final synchronization source is the survivor with the smallest jitter. So as you're looking at how the Ntp service election is done, we recommend that you use 3 servers, okay, in that process, because with just one server, like it says here in the bottom, the lower portion here, just one time source will always be trusted. If you got one server in your environment and you're running your whole corporation, it's always going to trust that time as long as it's Stratum 1. If it jumps down to, and I didn't touch on this earlier, but if it drops to Stratum 16, it's still providing time, but the clients are looking at that Stratum 16 time and saying, I see you have time, but I can't use you because I don't trust that your time is accurate. So the same thing can happen here. Just one time source gives you that process to get time. But if something happens to that clock, something happens there, you don't have a backup. You don't have another way to recover. You can't go to Stratum 2. You can't do anything. If you've got 2 time sources at the Stratum 1 level, what happens is you have 2 choices to make, and they'll make the choice, but you might be able to get better accuracy if you had 3 choices, because what happens with 3 choices is it looks at the 2, it looks at the 3rd one, it looks at the other 2 again, the last 2, 1 and 2, and then it looks at 2 and 3. Which one out of all of those has the best time is the one that it'll use. So for a 3 server configuration, a failing server will cause a two server problem to appear. So what happens is it sees that server B or C is messed up, and now since it's messed up, let me go ahead and use A or B. So it'll go back through that algorithm again for selection, and it'll limit your choice, but at least you have that choice within there. If you just have one, then you're going to go into an alarm state. So where I was talking about earlier, where like when you're setting up an NTP server within our device, here you'll see that this will be the NTP server. So this might be your Stratum 1 device here that you would put the IP address in. You have the min pole and the max pole set. And then you could enable iBurst. You could enable keys here so that you know that you have secure communication between your server and your Stratum 1 server and your Stratum 2 server, or your Stratum 1 server and your clients, depending on how you're using this. And then there's this mark preferred. So in the situation where you have the 3 servers, okay? If you've got 3 servers in each data center, you have those 3 servers, what you might do is mark the Stratum 2 and data server B as preferred in the B1. The C1 in this would be the preferred in the C1, but they would be paired together. So because there would all be Stratum 2s. So depending on what your infrastructure looks like, you probably want to do that, because this marked as preferred, if everything else is equal, that marked as preferred gives the nod one way to that device to become the time server. So that's basically just an added way to create the next to become the time server. So this clock hopping, that's what you could get when you got 2 time sources, where you jumping back and forth between them. You're going, hey, this is more accurate this second, this one's more accurate the next 2 seconds, and it's jumping back and forth. Typically, you want to stay with one device and then make sure that device, or as long as it's working, then you wouldn't have to go through and change anything. But to stop that clock hopping because of 2 devices, even when you got 2 servers, to stop that, you would say one of those devices and say, okay, this one is my preferred device. You see auto key is at the top, the MD5 and the auto key is at the top. Auto key was something that we used to use, that used to be there. It was never really used well, and it was never really implemented well. But the symmetric keys is really where everybody is now, and we no longer support that on the newer products. We don't support the auto key, but symmetric keys is there. So when you want to secure your communication, encrypt your communication between your server and your Stratum 2s, or your servers and your clients, or your servers and your switches, you can start using keys. From the monitoring, what we touched on earlier with the NTP Q minus P, if you were to log into our device into the web interface, you log in, you could run this command, and when you run this command, what you will see is the output down here below. So if you ran this on a secure sync server, you would see this. You can see the command here. You would see these items right here. These items here are the Stratum 0, so that's what's happening internally. We're providing PPS. This is getting the T-Sync PCI card. That's the driver that we use to run our internal clock. But this right here is the server. Now, if you notice, that's the same IP address that was put in up here, okay? So when you look at that, it's saying it's GPS, is the ref ID, the reference. You've got the Stratum level is Stratum 1. You've got the peer, type of peer, Unicash local. This is Unicash. When the last packet was received, 14. You got the pole, you got the reach, you've got the delay, the offset, and the jitter. So you'd see all of that information provided here. What I will tell you is that 377, when you're booting up type situations, that's an important one, because if you're not at 377, you're going to have some NTP problems. But if you look at this chart, Like if you look here on the front, right here at the edge, you'll see the star and you'll see the degree sign or the O, whatever you want to call it. So the star is the selected time reference. The O is the selected PPS reference. The plus here is a high quality candidate for NTP reference that can be selected by the NTP as the time reference. Good reference, but not selected. And then if we had an X here, it would be a false ticker. And then the outlier. So that goes back to the beginning where we were talking about the different things within the NTP protocol. Performance time differences of less than 128 milliseconds between servers and clients is required to maintain the NTP sync. So like I said earlier, you would have to go through the step process to get down to below that 128 milliseconds, then you can start to slew in. Time sources and network dependence, and typical internet accuracies of 5 milliseconds to 100 milliseconds. Within our device, you have a time offset graph in there. There's a number of different graphs that you can see, and you can look at it over time using this drag line here. You could drag that across, and you could expand it to take a look. We're going to get into the Ptp. Precision timing protocol, timing protocol. Ptp, it started off as used in the manufacturing environments. That's what it was originally created for. But because of its accuracies and the changes that were made, it is it's used in the commercial environments now, the banking environments, and a lot of your a lot more areas than when it started. Are there any questions, Chris? Do you know? Do we have any questions before we start in this?
Yes. One question: how is GPS 10 seconds of nanoseconds listed as more accurate than IRIG-B 1 microsecond? Isn't it the case that IRIG-B used GPS?
Yeah, so in the case of our device, so what you're looking at is GPS is going to be more accurate because it's coming right off of the satellites there, okay? But we have IRIG cards that are within our device. So when you take that Stratum 1 device that's connected to GPS and you have an IRIG card in there and you provide IRIG to another device, that's where those times are going to come into play. Same thing with the Ptp and the same thing with the half-quick cards and the static cards. When you move between, or when you select one of those cards or that protocol, you'll have that card, and those would be the accuracies that you're looking at between the client or server, or the point-to-point connection of the IRIG and the half-quick.
Thanks, Bob.
You're welcome. So if there's no other question, I'll continue on with the Ptp. So the Ptp protocol for exchanging of timing information between equipment connected through the network. It's an IEEE standard 1588. 2008 is known as when they implemented the P2P, the Ptp version 2. Before that, there was a version 1, and we'll see the next slide, touch base on that. Standards for a precision clock synchronization protocol for networked measurements and control systems. The protocols generate master-slave relationships among the clocks in the system. All clocks derive their time from a clock known as the Grand Master. And we'll touch base on all of that as we go forward. The Ptp clocks, the different clocks you have within the Ptp protocol, you have a master, you have a slave, you have a master slave, which is typically referred to as a hybrid clock. You have the transparent clock, and you have a boundary clock. So, and we'll touch base on all of that as we go through here. But I guess the main thing is the master clock is going to provide times to all your slaves. and the grandmaster is the big daddy of all of the masters. So what is a transparent clock? The transparent clock measures transit delays of a PTP message from one port to another port through the device and inserts the value into the message in real time. That's a mouthful, but essentially what it's doing is, as it's going through the device, it sees what that delay is, and it inserts it into the packet. So when it goes to the next one, it'll insert the next hop, it'll insert that delay in, and it'll continue to do that till it reaches its end destination. Transparent clocks do not generate their own PTP messages and are not PTP nodes, and lead to simpler PTP networks. So essentially, all they're doing is, it says, hey, I got this much delay within this switch, insert it in. I go to the next switch, I got this much delay. I go to the router, I got this much delay, and go to the next switch. And then when I get to my client, there was X number of milliseconds of delay through the process. So it's done by end-to-end. Delay calculations are made on the entire pathway from the master to the slave. Is done via peer-to-peer. Delay calculations are made on each network segment between the master and the slave. So so that in our device, that is a configurable way of how you want to measure. So if you decide, if you check the end-to-end, then you will do the end-to-end result. If you check peer-to-peer, then it will do the peer-to-peer way, the peer-to-peer way. The boundary clock, each port of a boundary clock implements a full PTP node. So essentially what happens is, when you come from our device out of our PTP master, you go into another PTP master or a switch or whatever a router, whatever it is you're going into. Basically, you go from a master into a slave, a master into another slave, a master into another slave. So that port becomes a full node. So masters on all ports are analyzed at once. The port connected to the best master will become a slave. So the port connected to the best master will become a slave. All other ports will become masters synchronized to the best master. Many may scale better in more complex networks with complex topologies. May have greater startup times as multiple levels of hierarchy are synchronized throughout the network. So that's one of the, I won't say a pitfall, but one of these sacrifices is that as you're starting this up, you have to allow the network basically to learn where all of the devices are and how it's going to, how each level is going to be affected as it synchronizes all the way through the network. So it just takes a little bit longer for it to learn the structure of the network. And you can see that laid out here with the boundary clocks and the transparent clocks.
Morgan, there's a question in the chat. How does PTP relate to CISC Ethernet as per eCipr?
eCipr?
ECIPR.
ECIPR.
Check out the chat box, you can see it.
I can.
You see the chat box?
Yeah, I see Q&A.
Yeah, the chat box. It's there.
So I'm not familiar with the CIPR to be able to answer the question, but I could take that one back.
Yeah, so that's from Stephen. So Stephen, we've got a note about that. We'll get back to you on that. Oh, sorry. Stephen's just put ECIPI, ECIPI.
ECIPI. I'm still not familiar with the ECIPI.
Same one. So Stephen, we'll get back to you on that one.
Yeah, we can. I can do some research or ask one of my colleagues, and get back to Chris with the answer, and he can provide that to you.
Okay.
So I was finishing up this slide. So basically, this is what the the boundary clocks network would look like, and similar to what the transparent clock would look like. So V2, almost all applications, most companies, including Orolia, we don't have V1 equipment. V1 equipment would be really old equipment, post 2008, 2006 timeframe kind of stuff. More than likely manufacturing, or like here, it shows you the V1, only 2 known applications, the INET, which is the US military test range, and then the older factory automation industrial controls. The difference between the 2 protocols is the V1, you see the sync, follow-up, delay request, delay response, and the management message. In the V2, you've got more packets providing more information. So you've got an announced message, you've got the sync still, you've got the follow-up and the delay request and the delay response still, but then they've added a peer delay, the peer delay response, and then the follow-up message, and then you still have the management messages.
Morgan, it's Chris, just a quick one. Yeah. Correction to that previous message, it may not help, but he was actually talking about eCPRI rather than that. So the real question was, how does PTP relate to Sync Ethernet as per eCPRI? Does that help, or do we still need to go back?
I don't know the answer to that, man.
That's okay. We'll go back and ask Stephen. No problem.
No, I know what he's saying, but I don't, I don't know the answer to it.
Okay, cool. We'll get back to that.
You got 2 modes for 2 transmission modes. You got multicast, which is similar to what we had in the broadcast within NTP. Different, but the multicast process is similar. So PTP messages are sent to every network element connected to the network. You've got specific IP address, IP multicast addresses. And so all of your multicast addresses, that 244.0.1.129 and the .0.1.107. You got Unicast, the PTP messages are sent to a dedicated Ptp clock. The destination address equals the IP address of the clock to be reached. And if you're doing Unicast, you'll want to have your server, you want to have your masters with a static IP address, because you don't want them changing with DHCP. And the time to live, in order to prevent dead loops within the network, they provide a time to live in the packet. So you should see that decrement as it goes through the network. And so I believe they start off at 128, and as it hits a hop, it'll drop to 127, and the next hop would be 125. If it get 26, if you get all the way down to 0, then it will discard the packet so that the packet just isn't continually being in this loop. So you've got, there's domains within PTP, and those domains allow you to segment the PTP network or the PTP devices that you want controlled by specific masters. So all PTP messages include a domain number. So when you look at within our device, you'll see the PTP, domain number there that you can configure. You can set that. I think we defaulted to 225 or something, but you can change that. You can change it to whatever you want it to be. Only Ptp clocks with the same domain number can interact with each other. So in the example here, what this is showing you is if you take the Ptp master M, that's for the master, and M1 and M2, the M1 is only going to communicate with the S4 and the S1. And the M2 is only going to communicate with the 5, the 3, and the 2. So even though they're all on the same network, they're all going through all of the same types of switches, the traffic isn't interfacing with each other because of the domain. So that's a way to segment and segment that traffic off your network or from or through your network. Ptp Port States. So you have the protocol, the Ptp protocol uses these two ports, basically the 319, the UDP ports for event messaging, and the 320 port for the general messages. The clocks are going to run in a master only, a slave only, and a master slave with the hybrid mode, like I said earlier. The state of the Ptp ports within the package itself will be those seven items here to be disabled, so the PT port is inactive. The Ptp port could be initializing, so the port does not have does not connect to the Ptp clock to the network, or the Ptp clock is initializing. It could be listening, so the Ptp port is listening for announce messages from the Ptp master, where you saw earlier where I mentioned about you sends an announce message. In passive mode, the local Ptp clock is master, but in standby and waiting. In that instance, you might have multiple masters on the network, and that's why it's standing and waiting in case of the grandmaster, and it demotes itself, and this one is ready to step in and become the master or the grandmaster when it's in passive mode. Then you got master, you've got the Ptp master is elected as the reference clock. So that election takes place and it says, hey, you're the grandmaster, you're the one. But you got one standing here passively waiting just in case something happens. Vice president, you know. The uncalibrated, a slave clock waiting for synchronization from the Ptp master clock, it has elected, and a slave clock, which is one that's synchronized from Ptp master. We'll touch on this in a moment, but the master, where that comes into play is the best master algorithm, and that's how the master gets selected. And that's how you have a device that's passively and waiting, and you have one that's listening mode. So you have all of those different things, and it's all done via the algorithm, the best master algorithm. Hence the next slide. At startup in multicast transmission mode, the Ptp non-slave, so the masters basically are the hybrid masters. So that would be the ones that's master slaves. The Ptp non-slave only clocks goes to master state and repetitively broadcasts announce messages, including information about the local clock level of confidence. So within that broadcast, you're going to see the clock class, the accuracy, the variance, the priorities. Those are settable, are user settable values to prioritize equipment one to another. So you can set that in the equipment so that you can say, I want this device over here to be the master. I want this one here to be it's a master, but I really prefer this device one in the data center here versus this other device in the data center. The Ptp slave only clock is directly listening for announce messages, and its status is listening, as stated earlier. The best master algorithm included in each Ptp clock derives from the announce messages, the comparison of the local clock, the local Ptp clock to the remote one, and decides to elect the master clock. This process is refined each time a new announce message is received or with timeout. So when you look at this, you've got two masters. The masters are talking to the slaves, and they're doing an election. So in this instance, the master M2 is higher quality than M1. It is in a master state. The M2 was in a passive state. So we talked about the passive state before, where it's standing and waiting to be the master. the slave, when receiving synchronization sync event messages from the PTP master clock M2, switches to slave state. So that master will switch to a slave state while it's receiving the information from the grandmaster, but it's still waiting via the algorithm to be the master should something happen to that grandmaster that's on the network. You've got, this basically takes you through the slave distance master, slaving to distant masters. So basically this is really what's happening on the protocol stack as you're going up and down the protocol stack. You got the clock adjustment process, compilation of time stamping information attached to each message exchange with PTP master. The reference the PTP slave clock issues. So it's got the instantaneous phase difference between the local clock and the remote PTP master. You've got the current frequency difference of the driving local oscillator regarding the remote PTP master clock. You've got the process update rate. The slave adjusts to the local time scale with the pacing of sync messages coming from the PTP master reference. So basically, this just takes you through the what's kind of happening in the stack there. At the physical layer, you've got the maximum time precision limited by media modulation schemes and physical coded data, and then you've got the network access layer, which is looking at your jitter. And then to get into the application layer, it's looking at the jitter with the software jitter. So these are all things that help the slave communicate with the master. And you've got Unicash utilization, Unicash initialization. So when you're in Unicash mode, all IP addresses mapping, all IP address mapping shall be introduced by operator. So you see over here, you've got the request announcement, the signaling, the acknowledgement here. Then you've got a request sync, then you've got the acknowledgement, you've got the delay response and the signaling, the acknowledgement. So as it's stating here, the opening of communication between the clock is initiated by the slave, which was done here. The slave clock receives requests, quality information from the PTP master clock. The slave clock sends a request for a sync session. So that's where we were here, the sync session. And each session is limited in time. The time can be set by the operator. So we can set the time within our device. And then this just really touches on the calculation, the math to do the drift in the two-step mode. And this particular one just touches base in two-step mode with the sync and delay request messages in that. And any questions? That's it for time. This is just a quick overview down and dirty.
So thanks, Morgan. I think we're a little over time. So if you've got any other questions, please email them to us and we'll deal with that. That was very interesting and informative, Morgan, especially the section on time and frequency distribution, as well as that coverage of both NTP and PTP. So everyone, that brings us to the end of today's webinar. Please also email us with your feedback of how we did and whether we met your expectations. And we'd like to hear from you about any other topics you might want us to cover in future. As I said at the beginning, a link to the recording of this session will be available within a day or two. So if there's anyone in your organization who's missed out and would like the link, just let us know. And of course, if there are any further questions or perhaps you'd like to discuss with Vicom and Orolia's positioning, navigation and timing solutions with us, please contact us. You've got our contact details on the bottom of the reminder email we sent yesterday. So thanks again, everyone. We'll sign off now. Thank you.